Lecture 10B on the calculus for parametric equations. The key to developing the forms for the derivatives for parametric equations is to think of y of t as a composition of y of x and x of t. So if we combine y of x with x of t, we end up with y as a function of x of t, which is y as a function of time. Now if we take the derivative, right, we're going to use the chain rule, so dy by dt is dy by dx times dx by dt. Fine. Now isolate dy by dx, and we end up with the expression for the slope, dy by dx, the slope along the curve in the xy plane in terms of the parametric equations, dy by dx, the parametric equations x of t and y of t. So let me say that again. We're looking at dy by dx, which is the slope of the curve in the xy plane. But the functions x and y are functions of a parameter t. So we can take the derivative of y with respect to t, divide it by the derivative of x with respect to t, and end up with the slope in the Cartesian plane. Of course, x of t cannot be equal to 0. So here's an example. So we have a circle. X equals 10 times the cosine of t, y equals 10 times the sine of t. We want the slope along the circle, right? So the expression is dy by dt divided by dx by dt. dy by dt, of course, is 10 times the cosine of t, and dx by t is minus 10 times the sine of t. Right? Substitution, okay, canceling the tans, we end up with the slope along the circle is minus the cotangent of t. But t cannot be any multiple of pi, otherwise the denominator would be 0. So those points are excluded. I'll show you a little bit which points are excluded. Well, so we have a circle here. Okay. The point where the derivative with respect to t is excluded is right here and right here. Of course, in those cases, the slope is actually vertical. Alright, those points. Otherwise, we do have the slope along the circle in the xy plane as minus the cotangent of t. When you go to evaluate the derivative, there are two cases. In one case, the value of the parameter is known. For example, if we had the equations that we had just a minute ago for the circle, and we wanted to find the value of the slope along the curve when t was equal to pi over 6, then all we do is develop the form dy by dx as a function of t. Notice that it is a function of the parameters, just like the equations were. Substitute the value of t and get our answer. In the other case, you want the derivative at a particular point xy in the xy plane, and you do not know the value of t, the value of the parameter that created that point, so you have to go find it. Right. So let's say we want to find the derivative at the point where x is minus 5 and y is 5 times the square root of 3. And we have to find the corresponding value of t. So look first at the x equation, and you want to find out what values of t would result in an x of minus 5. So we have to find out what values of t would have given us the x of minus 5. Then we go and find what values of t would have given us the y of 5 times the square root of 3. Right. In the case of x, so we're trying to find t. Remember, x was 10 times the cosine, hard to write with a mouse, times the cosine of t. Okay, so I solve for t, right here. T is the arc cosine of x over 10. That will give us 2 pi over 3 and 4 pi over 3. We're only going to go around the circle one time. Now we do the same calculation for y. We want to find the values of t such that y is 5 times the square root of 3. We find that there's two of them, pi over 3 and 2 pi over 3. From this list, we take the intersection between the values of t that would give us y, the required value of y, and the values of t that would give us the required value of x. In this case, it's, of course, 2 pi over 3 is common to both lists, and that is the t that we use to compute the derivative. This will then give us the derivative, substitution 2 pi over 3 into minus cotangent of t gives us the derivative at the point minus 5 and 5 square root of 3. I want to go over that procedure again. Just from the equations themselves, we can get an expression for the derivative as a function of time. If we want to know the derivative at a particular time, that is just a matter of substituting that particular time in for the value of the parameter t. If instead we want the derivative at a specific point in the xy plane, some point xy in the plane, then we have to go and find the value of t that created that point. Right? So to do that, we look for all the values of time that created that particular x value. Then we look for all the values of time that created that particular y value. We take the intersection of those two sets and find the time that's common in both of those lists, and that will be the time at which we are at that particular point in the xy plane. Use that time, evaluate the derivative at that time, and you will get the derivative at the point xy. It's also interesting to identify points along the curve. This is in the xy plane, these points that have a vertical slope or a horizontal slope. Okay. At a vertical slope, dy by dx is not defined. If you remember, I drew you the circle and showed you that at the points where the circle crossed the x-axis, the slope would be vertical. All right. The slope isn't defined at that point because dx by dt is equal to 0. So if we find the times at which dx by dt is equal to 0 and dx by dt is not equal to 0, we'll then found locations where the slope would be vertical. For the circle, the slope is vertical when n is t is some multiple of pi. At that point, dx by dt is 0, but dy by dt is 1. It is not 0. For a horizontal slope, dy by dx is 0. So now the conditions that we had for the vertical slope are now reversed. We need dy by dx equal to 0, but dy by dt equal to 0, but dx by dt not equal to 0. So let's go back to the circle again, and we want values of t at which the numerator, which would have been the cosine of t, was 0. And that would be, of course, 2n plus 1 pi over 2 will give us values at which dy by dt is equal to 0. At these same values, dx by dt is not equal to 0. It's at 1. That satisfies the criteria, and that's what you would expect from a circle. There's a circle here, sort of centered about the origin. Okay, so here we have those horizontal slopes, and that's what we're looking at in this on this slide. And here are the locations of the vertical slopes. So the criteria for the horizontal slope is that dy by dt equals 0, but dx by dt does not. The conditions for the vertical slope is that dx by dt equals 0, but dy by dt does not equal 0. To take the derivative, or the second derivative of parametric equations, we consider dy by dx as a parametric equation. If you remember from the circle, dy by dx equals minus cotangent of t. T is the parameter. So the slope, the first derivative, is also a parametric equation. We apply the same procedure that we did before, where instead of y, we use dy by dx. If you remember, for the first derivative, it's written right here, dy by dx equals dy by dt divided by dx by dt. But in this case, y, right here, is replaced by the first derivative, dy by dx. And that is the result you're seeing right here. So the second derivative, this is in the Cartesian plane, the curvature, equals the derivative with respect to time of the first derivative divided by dx by dt. Okay, if you can see that we have substituted another parametric form, dy by dx, for the y in this equation right here, then you will understand this one. You might think that the second derivative would be the ratio of the second derivatives of the parametric equations, and the answer is no, it is not that. In the numerator, you have, look at the pin here, you have the derivative with respect to time of the first derivative, and in the denominator, you have, again, dx by dt.